azimuthal quantum number. The azimuthal quantum number. Very important. The azimuthal quantum number. What is it all about? Azimuthal quantum number. The azimuthal quantum number. Basic information you will have to know, or you need to know rather, concerning the azimuthal quantum number. Number one, the azimuthal quantum number is conventionally designated with a small letter word L, as you can see it on the board. Secondly, the azimuthal quantum number is alternatively known as the secondary quantum number or the subsidiary quantum number, and most in particular, the angular momentum quantum number. Why do we call it the angular momentum quantum number? We call it the angular momentum quantum number because it describes the spatial distribution of the electron cloud in space about the nucleus, and also provides a detailed knowledge of the shape of the atomic orbiter. Mark that. Have it at the back of what? Your mind. The orbiter number 3. The orbital angular momentum quantum number. The orbital angular momentum, to be specific, according to what Schrödinger, is denoted with a capital letter L and can be obtained mathematically as L equals to what? You have what? H all over 2 pi, the root of L into bracket L plus 1. This is a mathematical equation deduced by Erwin Schrödinger fundamentally to compute the magnitude of the orbital angular momentum, where L is known as the angular momentum, H is known as Planck constant, and of course pi is what? An Archimedes constant. L is what we call the angular momentum quantum number. So with the aid of this equation, once you have the knowledge of the orbital angular momentum, you can as well estimate the value of what? The angular momentum quantum number, otherwise known as the secondary or subsidiary quantum number. That is point number 3. Point number 4, very, very important, very, very sacrosanct. The angular momentum quantum number was actually discovered in the year 1921 by Arnold Sommerfeld. Mark that, please. Angular momentum quantum number. The discovery is attributed to Arnold Sommerfeld in the year 1921 from his relativistic atomic model, a model which was obtained from the modification of the Near-Bohr's energy equation. Please, for detailed knowledge concerning the derivation of the Near-Bohr's energy equation, I will advise you to watch out for my video, which has to do with the derivation of the Near-Bohr's energy equation. So, talking about the angular momentum quantum number, like I said before, it was discovered in the year 1921 by Arnold Sommerfeld from his relativistic atomic model, which is a model obtained from the modification of the Near-Bohr's energy equation. Please have that at the back of your mind. Take note of the discoverer of each of the quantum number. It's very key. They may evaluate you based on that. Number 4, I think so. Point number 4. Another important fact you need to know concerning the azimuthal quantum number is that the azimuthal quantum number can only take values ranging from L, sorry, it can only take values ranging from L equals to N minus 1. That is to say, when N is equals to 1, azimuthal quantum number will produce N minus 1, which is equals to 1 minus 1, and that is equals to 0. When azimuthal principal quantum number is equals to 2, you will have azimuthal quantum number to be equivalent to, okay, let me make it in a manner that will be more clearer. The possible values that could be taken by the azimuthal quantum number ranges from, we have inside of the M principal shell. This could be established using the formula N L rather is equal to n minus what? 1. And that is equal to 3 minus 1. 3 minus 1 will produce what? 2. But before approaching 2, the possible numbers of the azimuthal quantum number becomes what? 0, 1, and of course what? 2. 0 corresponds with the first what subshell known as X, the 1 for the P share, and of course 2 is said to be the D subshell. Implying that inside of the M what principal share, there are 3 sub what shares or sub energy, and they are SPD rather. Now what about for a principal quantum number of what? N equals to what? 4. For a principal quantum number N equals to 4, that will correspond with what? N share. The question is, how many number of subshares do we have inside of what? The N share. Of course, it could be computed using the formula N is equals to N minus what? 1. And that is equivalent to what? 4 minus 1. And that will give us what? 3. But before approaching 3, of course, definitely, the possible what values will be 0, 1, 2, and 3. Where 0 corresponding with the first subshare, known as the S what? Subshare. 1 is for the P what? Subshare. And of course, 2 is what? The D subshare. And 3 is denoted with the subshare called what? F. So inside of what? The N what share, there are 4 what? Sub what? Atomic orbitals, otherwise called what? Sub what? Energy level or subshare, known as the SP, D, and what? F what? Subshare. Now, in summary, we can what? Establish a table to actually what? Reveal or disclose the various number of what? Subshares that are contained in each of the what? The principal what? Share. For instance, I think you are going to have the number of what? Subshares. Okay, let's say the principal what? Shares. We have the principal quantum number, principal what? Quantum what? Number, ranging from 1, 2, 3, 4, 5, 6. And of course, we have what? The principal what? Share. For 1, that corresponds with K, L, M, N, O what? P. Now, the azimuthal quantum number, which is N minus 1, will give us, for K, you have azimuthal quantum number of what? 0. For what? L, you have azimuthal quantum number of 0 what? 1. For N, it is 0, 1, 2. For what? N, 0, 1, 2, 3. For what? 5, which corresponds with the O what? Principal share is 0, 1, 2, 3 what? 4. Meaning that what? The subshares now, talking about the sub what shares, for O, it is what? 1x. Remember, it belongs to what? The energy level, otherwise called the principal quantum number what? 1. And that corresponded with the energy level 1, which is the what? The K energy what? Level or what? Share. So the subshare under what? The K is called 1x. Now for what? A principal quantum number of what? 2. Here we have the azimuthal quantum number to be 0 and 1. We have 2x, and of course 2, 1 being represented with what? P. Then for what? A principal quantum number of 3, which corresponds with the M share, the number of subshares becomes what? 3x, 3p, and what? 3 what? D. Then for what? M what? Principal share, which corresponded with the principal quantum number of 4, the number of what? Subshares are 0, 1, 2, and what? Of course 3. So the subshares becomes 4x, 4p, 4d, and of course 4f. Now for a principal quantum number of 5, which corresponded with what? The O what? Share, and with subshares and with what? Azimuthal quantum numbers ranging from 0 to 4, the subshare becomes what? 5x, 5p, 5d, and of course 5 what? F, and 5 what? G. So all of these are said to be what? The subshares, which is made possible as a result of the knowledge of the azimuthal what? Quantum number. So please, like I said before, this aspect or this what function as well performed by the azimuthal quantum number must not be taken for granted. Let us now consider another vital function or role as performed by the azimuthal quantum number. Number what? 6. With the help of the azimuthal quantum number, we can predict the order of what? Arrangement in terms of, or the order of increase or decrease of what? The energy as possessed by each of what? The sub shares. Remember, these are the sub shares. Experimentally, it has been what? Noticed that the azimuthal quantum what number has a slight what? Effect on the energy of what? The sub share. And this would account for the reason why the energy of X what? Sub share is less than the energy of what? The P what? Sub share. And that the energy of P sub share is less than the energy of D sub share. And the energy of D sub share is less than, let's take it like the trend. X is less than P, P is less than D, D is less than F. What does that imply? It implies as the azimuthal quantum number increases, the energy of the sub share also increases. And when it decreases, the energy of the sub share equally decreases. It implies that what? The azimuthal quantum number in a way impacts or affects slightly the energy of the sub share. Please have this at the back of your mind. Don't confuse it with the principal quantum number. Like I told you, the principal quantum number determines the energy of what? The electron in the atomic orbital, not what the energy of what? The sub shares. Take note of that, please. There's a distinction between what the energy of the electron in the atomic orbital, the quantum number that actually what determines it is called the principal quantum number. But when it comes to the energy of what the sub share, it is the azimuthal quantum number that what affects the energy of what the sub share in what the principal what share. The higher the azimuthal quantum number, the higher what? The energy of the sub share. And the lower the azimuthal quantum number, the lower the energy of the sub share. Please don't confuse this with what? The role played by the principal quantum number in regards to what? Energy. Take note of that. What the principal quantum number does with respect to energy is that it determines the value of what? The electron it determines the energy of the electron in the atomic what? Orbital, not what the energy of the sub share obtained from what? The principal what share. It is the azimuthal quantum number that what affects slightly the energy of the sub share in the what? Atomic what? Orbital. What does that imply? It implies that what? As the value of the azimuthal quantum number increases, there will be a corresponding increase in the energy of what? The sub share, and vice versa. That is to say, the smaller the value of the azimuthal quantum number, the smaller will be the energy of the sub share in the atomic what? Orbital. And this will account for the reason why the energy of what? The S sub share is less than the energy of the P sub share. Why the energy of the P sub share is less than the energy of the D sub share. And of course, the energy of the D sub share is less than that of F less than that of G less than that of H, and so on and so forth. This is as a result of the impact of the azimuthal quantum number. Have that established at the back of your mind, and don't confuse it with what? The energy possessed by the electron in the atomic orbital. It is the principal quantum number that does that. But as far as what the energy of what the sub share is concerned, it is the azimuthal quantum number. Another vital knowledge you need to know concerning the azimuthal quantum number is that the azimuthal quantum number denoted by small letter L is in a way related to the energy of the electron cloud, otherwise known as the atomic what? Orbital. In this case, the eccentricity of what? The ellipse can be what? Obtained using the formula that says L plus 1 all over what? N is equal to B all over what? A. This is the formula by means of which the eccentricity of the ellipse can be what? Obtained. Therefore, in conclusion, it can be said that the azimuthal quantum number determines the angular momentum of what? The atomic orbital. Hence, the shape of the atomic orbital. It is in view of this knowledge that we today can conclude conclusively that what? For n equal 1, we have azimuthal quantum number of n minus 1, and that is equals to what? 1 minus 1, and that is equals to 0, which corresponds with the x subshell, otherwise called atomic orbital. And this is a letter used in representing what is called the sharp atomic orbital. And the shape of the sharp atomic orbital is known as spherical shape. This to be what revealed as a result of the knowledge as of what the azimuthal quantum number. Now, when n is a principle of this, then I ask you an examination condition: which of the quantum number determines the shape of what the atomic orbital? I said it, and I'm reiterating on that again. It is the azimuthal quantum number. For what is for n equal what 1, azimuthal quantum number is equal to what 0, and that corresponds with what the s what subshell, otherwise known as the s atomic orbital, that is known as the sharp atomic orbital. This shape is spherical in shape. It is spherical in shape. When n is equals to 2, you have n to be equal to n minus 1, and that is equal to 2 minus 1, and that corresponds with what is called the p atomic orbital. And the shape of the p atomic orbital is called dumbbell shape. Dumbbell what? Shape. Dumbbell what? Shape. Take note of that. The shape of the s orbital is spherical shape. S is known as sharp atomic orbital. Which shape is what? Spherical in shape. Which shape is what? Spherical. Now what? The p atomic orbital is known as the principal atomic orbital. Which shape is dumbbell shape. Then when n is equal to 3, you have n to be equal to n minus 1, and that is 3 minus 1, and that will produce what? 2, which corresponds with the d atomic orbital, known as the diffuse atomic orbital, and which shape is double dumbbell shape. Double dumbbell shape. I've seen this severally under examination condition, most especially this competitive examination, where students will ask, what is the shape of what the d atomic orbital? The answer is double dumbbell shape. And of course, for now, when n is equal to what? 4, I think we are going to be having n to be equal to n minus 1, and that is equals to what? 4 minus 1, and that is equal to 3, which corresponds with what? The n atomic orbital. The atomic orbital is known as the fundamental atomic orbital. Which shape is complicated shape? So please bear this at the back of your mind. I want you to have an ingested and digested knowledge of this, especially the shape. Take note, it is the azimuthal quantum number that will reveal to us the shape of what the atomic orbital. And this atomic orbital in summary are the s orbital, known as what? The sharp orbital, which is spherical in shape. You have the p orbital, known as the principal what? Atomic orbital, which is dumbbell in shape. Then you have the d orbital, otherwise known as what? The diffuse atomic orbital, which is double dumbbell shape. And of course, you have the s atomic orbital, alternatively called the fundamental atomic orbital, which is complicated. It is complicated in what shape? In other words, the shape is what? Complicated. I think with this, I have come to the end of all you need to know concerning the azimuthal quantum number. The next we shall be considering, which is also very sacrosanct, I mean very, very fundamental or key, is known as the magnetic quantum number.